Hello, for those watching on the recording, I'm David. I'm the coordinator of the Maths Learning Centre here at the University of Adelaide. It's semester 1, 2025, and this is the revision seminar for Statistical Practice I. And I've been asked to talk about all the different tests that are involved in the course. And before the recording started, we did a bit of a brainstorm and a quick scroll through the various modules in the MyUni. And we've come up with this list of the things that are in the course. And so we're wanting to talk about kind of like the general method for solving them, but also for deciding which one to do. Okay, well, we'll see what we can get through. If I don't get through them all, I apologize. We've got about an hour and a half left, and we'll see what we can do. Okay. So we've got a nice brainstorm here, and we can keep track of what we're doing. But the most important thing I need to say to begin with about making the decision of which one to do is that it is based on what the story is and the information in the story. So you'd be familiar with this now, every exam and test and assignment question will give you a little story about what the data came from, right? They'll say, oh, there were rats, or there were people, or there were dugongs, or whatever they are, and it'll give you a little context, and you'll read the story, and it'll tell you how the data was collected, and the kinds of things that were recorded on each individual. And so the very first thing that you need to do to make a decision about what to do with statistics is to know the story. Without the story, nothing will make sense. And they always ask you at the end of your exam question to interpret the results in context. And without the story, you can't know the context as well. Okay, and the story will tell you what the purpose was, usually, not always. So there are some things in there. There'll be a purpose. There'll be a question that is trying to be answered. That's what the purpose is. So there's a question the characters in the story want answered. And I usually call it a research question that they want an answer to. And it's important to know what that question is. That's the purpose. You need to know the subjects. So the subjects are whatever people or animals or houses or petri dishes or whatever it is that they are the things that have had data recorded about them. That's what you need to know. And you need to know what the data that was recorded them is like. And in particular, what that means is the variables. And these things together should be enough information well, not just the variables, but also how the variables belong to the subjects, basically. I don't know how to say that at this time, but yes, you need to know these things. Once you've got those things, you can make a start of making sense of the question you've been given and what you're supposed to do. And there will also be, as well as the story, instructions to you of what to do, right? We'll say calculate a test statistic or whatever. So separately to that, there'll be the instructions, but this is the story. And the people inside the story have a purpose of their own. And that's really important. So that's what you have to do first. Read the question and find that out. I wish I had a textbook with me to pull out some random questions and show you how that's done, but I'll make some up along the way. So when you do that, the individuals, the subjects, it's very useful to focus on the subjects and focus on the data that's been written down, the variables that's written down on them, and what kind of variables they are, whether they're categorical or numerical, will make a big difference. That they call them quantitative in this course, don't they? Yeah, but they do call them categorical. Yeah. So there's two different flavors of variables, which are categorical variables or quantitative variables. And categorical variables are designed for putting things in categories, so I draw them as boxes. And quantitative variables are numbers, and they're measured on some sort of scale. So these are the two different kinds of variables that there are. If you're looking for... so categorical variables do come in two different flavors, ordinal and nominal. I don't know if that's in this course, but it is in some courses. And quantitative come in two different flavors, discrete and continuous. But that generally doesn't make much of a difference to this sort of bit where you're choosing what test to do. So it's just categorical and quantitative that's the most important thing. And you also need to know where these fit in the explanatory story. Okay, so almost all research questions are about the relationships between things. But does changing which category you're in, the situation you're in, make a difference to the number outcome? That's often the question that you're asking. But it could also be, does changing which category you're in make a difference to the category outcome? So it could be, does being from a different country, which is a category, make a difference to whether you can smell asparagus or not, and that's a category as well. So those sorts of things make a difference. And also whether you've measured the same outcome more than once on each individual. That's important as well. Okay, so I draw these things as pictures, and those pictures help me to make the decision of which one is which. And so I'm just going to do an example of a story. People who visit a restaurant. Come from 3 different continents: Asia, Europe, and Australia. Well, Oceania, yes. Do they still call it Oceania? Anyway, that used to be, when I was at school, the name for Australia, New Zealand, Papua New Guinea. Asia, Europe, and Oceania. And they each have a favorite drink. Is there going to be a drink? Sure, let's it be a drink. And they're going to be soft drinks because I can't be bothered. Coke, Sprite, Fanta. It's one of those restaurants that does Coke brands. And so Waiter wants to know if she can guess. The continent from the drink. It's a stupid story, but that's the idea. And so what we have is the purpose here to see what the relationship between continent and drink is. We have 2 different variables that have been recorded on each individual, and they're both categories. And we have continent and we have drink. and we are interested in how they're related to each other. And my subjects are the restaurant goers. And so we have that we have whether we can use Coke, Sprite, or Fanta to predict Asia, Europe, or Oceania. That's what we're interested in. And each person's in only one of these categories, right? They each have a favorite. And that's a picture of this story. It's not a very good story, but it's the picture of this story. And so what we're interested in is the relationship between two sets of categories. Here's another one. A medical researcher has the existing just a second. No, I'm changing the question. Hello. Medical researcher wants to compare. Oh, did I actually start the recording? Yes, I did. Okay. Medical researcher wants to compare the effectiveness of Nurofen versus aspirin for fever relief. They give, 30 Nurofen and measure the change in temperature. And 30 people aspirin. And change in temperature. Something like that. And so I think about the individual people involved here, and they each have two pieces of information about them. We've got written down whether they had Nurofen or aspirin, and we've got written down their change in temperature. And so we have Nurofen versus aspirin, that's the drug. And everybody's only had one of those. Different people are in the different groups. And then what we've measured is change in temperature. And that there is a number. Yeah. And so this is the story that is happening here. And we're interested in how this is related to that, which is why I've got this arrow here, about whether we can use this to predict that. And so that's the information you want to pull out of every story. And that act of reading the story and getting the information out of it is something that you can practice completely independently of actually solving the problem. You can make sense of what the story is trying to tell you. And it's really important to make sense of what things you've recorded about every individual person. It doesn't have to be people, of course. There could be individual days or individual animals or individual petri dishes or individual houses or whatever. It's important to sit down and think about what has been recorded about each individual one of them. Okay. I hope that's a useful thing to say at this time, but that's the first step. You have to read the story and make sense of the story. Okay, so these two situations are quite different to each other. This one is a relationship between two categorical variables, and this one is a relationship between a categorical variable and a numerical variable. And that makes a big difference to how you're going to analyze them. For a start, numerical variables, you can calculate means and standard deviations of those. But for a categorical variable, you can't do that. All you can do is count how many are in each category. And that makes a difference to how you can analyze the data. And that is why we have different hypothesis tests. So the first thing to know is what situation each of these hypothesis tests goes with. So I'm going to draw them all on one page, and then we can talk about the details of how they work. Let's see if I can fit them all on one page. I do have them all on one page here. Okay, now I will say not all possible combinations of categorical and quantitative variables and how they're related to each other are in this course. There may be other ones that aren't in this course that you may find in a future statistics course, but they're not all here. All right. So we've already seen two of them. So one of them is, wait. So these ones are about relationships. It is possible to tell a story that isn't about relationships at all. It's just about a single variable. And before I move on, I just want to tell a story that might be about a single variable. So factory owner wants to know if their bottlenecking process with an average capacity of 2 litres like it should. So that's a story. We've got our factory owner. The individual subjects are the bottles because the information we have about the bottles is their capacity. And we're asking the question, so we have individual bottles. There we go, that's a bottle. And the thing that we've measured about our individual bottles is capacity, which comes in litres. And so it's a number. And so each individual bottle just has that number that belongs to it. And that's it. And the question we'd like is, what's the mean? Because the average is the mean. So it's not about the relationship between two different numbers. It's just about a single number all on its own. That is a different kind of story to the ones we've had before. So most scientific research is about relationships between things like this, like these ones that we said here. But quite a bit of quality control research is about just a single number. Okay. So we need to know how to do those things. Now, again, I'm just going to make clear to those listening and to everyone in the room, I am basing my list on what we did when we did a quick scan through the My Uni. I may have missed some, so if there's some on your mind that I don't say, please bring them up when I get to the end, okay? Because I can't, this course changes every year, and so sometimes the list of tests changes. Okay, so the situations that these go with is the thing I'm going to write down. So the first situation is when you have a single number and you're interested in what the mean is. Right, each individual subject has just one number recorded on them, and you're interested in what the mean of that is. And if your question is, so the question is, Actually, I've got an even better way of drawing it. Do you know what a mean is? A mean is a single number that does a good job of predicting the individual things. So is this mean a good way of predicting where the center of this data is? So that's the question. And if your question is that, is the mean equal to a specific number? Then there are two situations in which you might be. One is if you already know what the proper standard deviation is, and one is if you don't. So we know true standard deviation, and this one we don't know true standard deviation. This one is the z-test for a mean. And this one is the t-test for a mean. And if you like, some people call this the one sample t-test. That's what you said it was called, wasn't it, in this course? The one sample t-test for a mean. That's the situations in which they happen. We will talk more about how to do them a little later, and I promise I will, but I just wanted to talk about what situation they're in. So stories about either of these will mention just one number that's recorded on every individual subject. That's an important thing to know. Every individual subject just has one number, and there's nothing to predict it with other than the single mean. So in this story, just here, my bottles had one number, which was their capacity, and I just am interested in the single mean. I'm going to redraw this. Is that mean 2 liters a useful way of measuring, of predicting the capacity? And there is another situation in which there is only one variable, and it is this, where you have categories that are either yes or no. And the thing you're interested in is how likely it is to say yes. So a story of this type might be poor education researcher is interested in what proportion of children actually do any of their homework. And so they did a survey. Oh, my chair went down. They did a survey and asked and asked every child, and some of them did their homework and some of them didn't. They wanted to know if more than 50% did their homework. And so there's two options for each child. They either did or they didn't. And then you say, what's the percentage that are in this particular box? So it's actually much more that proportion of being in that thing. And a proportion is a percentage, but as a decimal. And this is the one sample z-test for a proportion. Yay. I have a question, and hopefully across all of the people who are here, you can answer it. When they did chi-squared tests, did they do a chi-squared test for goodness of fit? Yes. And they also did the chi-squared test for association? No. That's interesting. That would be something that was worth looking in your My Uni to see if they did that, because there are two different situations. Okay, no, they have. Cool, thank you. That answers my question. So there is another situation where there's only one variable, but that variable could have any number of categories. And instead of a single proportion of the one that's in just yes, there's like a list of proportion. So we're going to say, is the proportion list of proportions, so we've got 4 different options. Maybe they're the favorite drinks again. And you want to know, is it 30% this one, 20% this one, 50% this one? That's the question that you're going to ask yourself. That whole list, is that the right list of proportions? That is the chi-square test for goodness of fit. The reason it's a chi-square test is it belongs with a categorical variable. Chi-square tests go with categorical outcomes. And it's the thing that we're interested in, whether it fits goodly, is that list of proportions. Does that fit my data? So both of these go with having one categorical variable measured on every individual subject. It's just that this categorical variable is just yes or no, and this one is a list of different options for each one, but each one's only got one option. Yeah. And interestingly, you can do the chi-square test for goodness of fit in this situation as well. It's just that if there's only 2 options, then if there's 20% in the other one, there's 80% in the other. In one, there's 80% in the other. So you can do them both. Also, the goodness of fit, the Z test for proportion can produce a confidence interval, but the goodness of fit one doesn't. So that's a whole other thing. Okay. So these are all of the tests that go with a single outcome on each individual. These ones go with numerical outcomes. These ones go with categorical outcomes. This one, knowing the true standard deviation, is very rare in real life. And so your lecturers are much more interested, usually, most statistics lecturers are much more interested in you knowing how to do the t-test. And so it's very unlikely for this to appear in an exam, because they want you to be able to do this one. Yeah. Okay, so they're the situations where there's only one thing measured on each individual. And that's the tests that go with them. How they work is a different question, but I just wanted to do the decision making. It's page 5. So the next question is, what if there is a relationship between 2 variables? So here's my pictures I'm going to draw. If you have a categorical outcome, it doesn't matter how many categories there are. And a categorical explanatory variable, it doesn't matter how many categories there are. And every person is in only one of these categories. So for example, they could have come from at most one continent, right? That situation where you're interested in whether being in a different category here makes a difference to being in a different category here. So in my original example, it was coming from a different continent making a difference to which drink you prefer, but it could just as easily be which course you study at uni, making a difference to whether you agree or disagree to the lecturer doing a good job. It could be these might not be people, but they might be animals, and these are 3 different treatments that you give them, and these categories are whether they, are alive or dead after the experiment, those sorts of things. those sorts of situations are what the chi-squared test for association is for. If someone says the chi-squared test and they don't tell you what chi-squared test they usually mean the chi-squared test for association. All the chi-squared tests are designed for when there's a categorical outcome. For where the thing that you're interested in, whether it changes in different situations, is a category. So the chi-squared test for goodness of fit has a categorical outcome, but there's nothing to explain what makes it different. It's just there. Whereas the chi-squared test for association has a categorical outcome, but there are different situations in which that might be different. Okay. You may also not be completely sure which direction this goes, which one causes which one. That's fine. The statistics never knows which way the direction goes. The computer can't tell what order the data was collected in. So even though the arrow, I put it one way because that's how the question usually appears in the assignment, the statistics can't tell which one causes which one. That's not a thing that statistics can do. That's what experimental design is for. Okay, so that's that. I do really want to have one more look to see if there's z-test for two proportions. There is? Okay, good. I'm so glad. I'm going to add that to my list here. Okay. In the very specific situation, so this could have any number of categories. In the very specific situation where there's only two categories that it can be, yes or no, and there's only two categories that this can be in here. So for example, there's two treatments and the people either survive or they don't, for example, or there's two different classes and the students either pass or they fail. If there's only two options, for what could happen as the outcome, and there's only two situations to compare, then you can do the chi-square test and it will totally work. But you are also able to focus your attention entirely on the proportion of which come out as yes, and do the z-test for two proportions. So I know it's confusing that these two stories can be done, because this story is one of those. I know it's confusing that they can be done either way. Your lecturer, because it's a bit confusing, will usually tell you which one they want. If they want you to do a z-test for two proportions, they will tell you. Yeah. Plus, the z-test for two proportions is much easier to do by hand than the chi-squared test. There's a lot less subtracting, and therefore the answers are easier to calculate and get right. But think about the story that's being told and go, for each individual in this story, do they have just two outcomes, and are there two situations, and I'm comparing how likely it is? And if they use the word proportion, then they definitely want you to do a z-test of two proportions. That is 100% true. Okay. So you'll notice that when you do proportions, they always come out as z-tests. And I know there's one situation with numbers where it comes out as a t, as a z, but that's a coincidence. It's just that the z distribution happens more often. Okay, so these are the ones that have categorical outcomes. And then if you want numerical outcomes, where there's a number outcome that we're interested in changing, if there's two categories, two situations that the people can be in, or the dogs or cats or fruit flies or petri dishes or whatever they are, if there's two situations your subjects can be in and there's a numerical outcome, and you want to see whether they're different in those two situations, then that is what the t-test is for. This is the two-sample t-test. That's what it's for. And usually, though not always, they won't mention it, but usually they mention that we're interested in the mean and how that is different before and after. But they may not mention that word, and they'll still mention means in the data analysis. Or your original data will just have a list of numbers and you're just going to do the t-test and it will spit out means along the way. There is another situation that looks identical in terms of the story, it looks identical. This situation, there's still two situations, there's two categories that the subjects can be in. It's just that every subject is in both categories. For example, you get your participants to have Nurofen and you get them all on a different day to have aspirin as well. And you measure the change in temperature for both situations. If every individual has been measured in two different situations and every individual is in both categories, then what you're doing is a matched pairs t-test. And the matched pairs they're talking about is the pair of measurements that belong to the same person. So these two, in terms of the research question, are the same. You can ask a research question of, does Nurofen versus aspirin make a difference to your body temperature? Make a difference to your body temperature. And you can set up your experiment to either have a whole group of people with Nurofen and a separate group of people with aspirin, or you can give everybody both and measure their temperature twice, change in temperature twice. Those two situations are the same research question, but the data set up different. And that's the two ways of doing that. And then, what if you had multiple categories instead of just two? And everyone's in a different one. Still a numerical outcome, but instead of just Nurofen and aspirin, you have Nurofen and aspirin and Panadol, for example. This is what analysis of variance is for. It's like the ordinary two-sample t-test, it's just got more categories simultaneously. And the calculations you do are different, but in terms of the situation you're in, it's not that different to this. You may notice that technically we could have it with every person in all three categories. That's not something that's been covered in this course. Though if you do any future statistics in various different degrees, you may come up against it. And it's called repeated measures ANOVA, what the matched pairs version of ANOVA, but it's not matched pairs because there's three, so it's like matched triplets. So we don't call it that, we call it repeated measurements. Yeah. And then I didn't write it on my previous list, but there is one more. There are two more situations that have been mentioned as I will scroll through the notes. And they are these stories. Oh. So, damn it, I've forgotten which one I was going to do. I know there's two of them. Oh, no, I'll put it back and then maybe it'll help me remember. Oh, yep, I've got it now. Yep. Okay. There's two more situations. One situation is this, where you're still trying to predict a numerical outcome. but the thing you're predicting it with is not a category, but also a number. So instead of trying to predict people's change in body temperature with a specific drug, maybe this time you're trying to predict their body temperature with the dosage. How many milligrams of drug is there? Maybe this time instead of predicting children's heights from where their parents were born, you can predict their children's heights from the heights of their parents, for example. So if you've got two quantitative variables, then that is what regression is for. Now, regression does more than just answer yes or no questions about whether there's relationships. But along the way, there will be p-values in the regression output, and they will answer the yes or no question. And then the other numbers will answer the what's the formula question. So that's what regression is for. Technically, it's simple regression because there's only one thing predicting the outcome. In the future, you may do multiple regression where there's multiple different things predicting the outcome. But you did do in this course, they did mention once, what if there were two things predicting a numerical outcome that were two different categories? So what if simultaneously you had people what if you had two of them? What if you had you gave them a drug and you also had them in age categories of like over 50s and under 50s, for example? That's called two-way ANOVA, which was mentioned in at least one of the videos. I have a feeling it's probably not in the exam. I would very much recommend going and watching your lecturer's final week videos because they'll probably mention which things aren't examinable. In past years, the lecturer has said that two-way ANOVA won't be in the exam, but I don't know what this year's lecturer will do. But I'm just going to say it now that that's what's happened in the past. Okay, they are all of the stories that you've been given. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 stories. 11 different kinds of stories that you can come across. And a really good thing to practice is to pick any question in any stats textbook that you've got in any of your workshops. Do they have workshops in this course? Practicals. Any of the practicals, any of the seminars, look at the stories that go with those questions and any of the assignments and see if you can figure out which of the 11 stories it is. And it's based on what variables are recorded, whether they're categorical, whether they're numeric, whether they're quantitative, how many categories they've got, whether it's 2 or more, and how they're related to each other. So it's really interesting. You've only got one matched pairs situation. It is, in fact, totally possible to do a matched pairs Z test for proportions as well, but that's not in this course. Right, so there's lots of, if you start looking at these pictures, you go, what would happen if these were both the same, like going to the same group? It can be done, but they're not always in your course. I do know that they have mentioned on top of this non-parametric tests, and I should do them now. Non-parametric tests go with the same situation as these tests that we've already mentioned, but when the data can't be thought to be from a normal distribution. So if you ask this question, does being in a different situation make a difference on average to this number? Normally you would do the two-sample t-test in that situation. But what if this data isn't from a normal distribution, it was from something that wasn't normal? Technically, this one requires this to be from a normal distribution. That is why they invented the non-parametric tests. Now I just have to check. This one Some people call the Mann-Whitney U-test, and some people call it the Wilcoxon-Rank sum test. Which one did you have? Mann-Whitney? The reason I say both of them is that they were in fact invented by two different, like Mann and Whitney, and then another person invented these two different tests and published them in the same year. And then it turned out later that they always give the same p-values. It's amazing. I think it was in the 70s. Could be wrong. You know that it has to be like after 1930 that they were invented because they've got names. The really early tests don't have people's names on them. They're just called the t-test. So the ones with names on them are more recent. Yeah. Okay, so that's the Mann-Whitney test. And it is designed to answer the same question as the two-sample t-test. Does this numerical outcome, is it different in these two different situations on average? But the calculation you do in this one is based on this being a normal distribution. And the reason, because the p-value is a probability, it has to come from a distribution. So this p-value comes from a normal distribution, and the p-value here comes from rearranging the data in a different order. That's where the probability comes from. I don't know if they mentioned any other ones. Oh, they did multiple linear regression too, did they? Of course. But there's no other non-parametric test, just the Mann-Whitney? Yeah. But just so you know, the other ones have one as well. Technically, ANOVA is based on a normal distribution as well. And there's a version of this for not normal distributions called the Kruskal-Wallis test. And there's a version of this as well. So most of the things that are based on normal distributions have a non-parametric version. But you have to know what it's called in order to do it, like who it's named after, because they're all named after people. Yeah. But in this course, it looks like Mann-Whitney is the only one. And so the decision for this one is that it's not a normal distribution, and that's what makes you want to do the Mann-Whitney U-test. Okay, and you said multiple regression? Well, that's okay. That's just the same as ordinary regression, but there's more than one thing affecting the outcome. Like that. And ANOVA is similar in vibe to the multiple regression. It's just that these are categorical variables, whereas multiple regression, these are usually numerical variables. If you do any more statistics after this, then you can have mixtures of categories and numbers together. Yay. Okay. So there you go. That's the list of all the stories. And I'm so glad. Thank you so much, everybody, for banding together and getting the full list of tests that are in the course. So we've now gotten ourselves up to 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 now. You poor people. The people in the economic statistics course, which I did their revision seminar last week, they only had 8. So sorry, guys. All right. So that's all the situations. And it's a really useful thing, even if if you just pass this exam and go, look, I never want to do statistics again. At least you can know that the way to decide whether the right statistics has been done is based on the story in that way. Because then you can read a journal article and go, well, this is the story of what they've done. Now, that sounds to me, based on the fact that they've got a numerical outcome and 3 different groups, sounds to me like an ANOVA, but what they've done is z-tests for proportions. Oh, that's bad. Okay, so that's the sort of thing that you can do, is you can read an article and decide whether they've done the right thing, just based on the story. I hope that feels helpful. Yeah. All right, so now we've got about 45 minutes, and I'm going to talk about the details of some of those things. Okay. Now that one, oh, yep, we've got a new one. Oh, cool. They said that multiple linear regression is not examinable. in 2025, in case this semester 1, 2025, in case that changes. Cool, but they wanted you to know that it was there, your lecturers. Thanks for confirming that. That's why it's good to meet students who are in the course, because they might have noticed something that you haven't. And we've got another one here. Is there a situation where more than one kind of testing would be more suitable than the other? Okay, so whether you've got several different options for what kind of tests to do and one of them's better than another. Yeah, it is classic exam question is to give you some information and you have to decide whether it's a matched pairs t-test or an original recipe t-test, like a two-sample t-test. And one of them is definitely more appropriate than the other. To be fair, I have never read an exam question where they made you choose where the answer was the two-sample t-test. But please don't base it on that. Like, if it's possible to calculate, like if every individual has two measurements for them, and therefore it's possible to calculate the difference before and after, then it's a matched pairs. So yeah, and it is technically possible to, I have seen in one exam once, one where they gave you both of these and they gave you a graph that helped you decide whether it was normal or not, and then you chose which of them was the right one to do. These are very similar in terms of the situation that they're in. And the only difference between them is whether it's normal or not normal. And so you could be given a graph. I believe it's a QQ plot in this course. Is that right? Yeah. You're given a QQ plot and you'd look at it and go, oh, that's not straight. And so you'll do the Mann-Whitney U-test. Yeah. So does that answer your question? Okay, cool. All right. Well, let's look at some of the details. Let's have a look at all of these together. So for our Z-tests and T-tests, all of our Z-tests and T-tests, and even the T that comes out of a simple regression, because when you do the simple regression, you do the hypothesis test involved with a T. There's a T-test in here. The T-test on the slope. All of the ones that are T's or Z's, the calculation has the same shape. And so it would be useful to, I think, talk about that. So Z tests and T tests all work in a similar way. And all hypothesis tests have at least one idea behind them. All have the same big idea behind them, and Z-tests and T-tests have another smaller idea that the calculation is. So in fact, I'm just going to go back a bit. This may end up on the beginning. Let me go back a bit and say that hypothesis testing is based on this idea. You have your research question. Okay, that original question that's part of the story. So the story has a research question. And that research question is usually about whether a particular number is a specific thing. So is the mean 2 liters? Is the proportion 50%? Okay, so it'll be a research question. And what we need is a yes or no research question. Hypothesis testing can only answer yes or no questions. It cannot answer any other kind of question. So if your question is, how are these related? Hypothesis testing cannot answer that question. It can only answer, are they related? Does So yes or no questions. So that is the beginning of hypothesis testing, is to have a yes or no question. And you have to pick one of the answers, yes or no, and that is the null hypothesis. And the reason you do that is because of what comes after. So I'm going to leave a gap here. So what comes after is that you collect some data, right? You're going to collect data. And from that data, you calculate a test statistic. And a test statistic is a single number that you get from all of your data. One number. And what you do is you imagine all possible data. You don't really, but you imagine all the data that could have been collected. So if you had 30 people in your study, 60 people in your study of with the Nurofen and the aspirin, you imagine all possible sets of 60 people that you could have collected data from. You imagine all of those, and you imagine all the test statistics. And what you do is you compare your test statistic that you got today with all of the test statistics that could have happened. So we imagine we collect some data, we make a test statistic. Then we imagine all of the data that could have happened and all of the test statistics that could have happened. And we imagine what is ours compared to those. And if ours is unusual out of all the things that could have happened, then we are worried or happy, depending on what the goal was. Okay? But the only way to imagine all of the possible test statistics is to pick an answer for this question. And you have to pick an answer for this question that only has one possible way to do it. Because otherwise it's just too hard. So you have a null hypothesis with one way to be. I will make that clearer in a minute. But if your question is, for example, is the mean 2 liters? Then there is only one way to be 2 liters. And there are many ways to be not 2 liters. So your null hypothesis is the mean really is 2 liters. But if your question was, is the temperature different in the two drugs? Well, there's lots of ways to be different. There's only one way to be the same. And so the null hypothesis is that they are the same. That's how you choose a null hypothesis. It's the one that only has one way to be. And there's only one way to be the same. And there's lots of ways to be different. So it's generally about sameness. But I will say, if your question is, are these two things related? There's in fact lots of ways to be related, but there's only one way to not be related. Like if they're not related, then there's only one way to do that, which is to not be related. And so if your question is there a relationship? The answer is, the null hypothesis is no, there is no relationship. So I just want to say that. Sameness or no relationship. And so you imagine that, you pick a null hypothesis and you imagine that null hypothesis. You think, well, what if that null hypothesis is true? And we imagine all the data that could have been and all the statistics that could have been. And when you imagine all of the things that could be, what you're doing is calculating a probability distribution. Probability distribution is a description of all the things that could be and how likely they all are. And so this may not look like this, but this is a probability distribution. And then you compare your test statistic to that probability distribution and you get a p-value. And if that p-value is really low, then you go, that's a surprise. I don't believe this null hypothesis. But if that p-value is really high, you're going, Cool, totally possible. So null hypothesis could totally be true. I have no problems with that null hypothesis. So if this is low, then you are worried about that null hypothesis. So the p-value is in some sense a measure of how well your data matches the null hypothesis. And the lower it is, the less your data matches. Do not say it that way to a statistician. Do not say, oh, that's really low, so my data doesn't match the null hypothesis. Actually, that's probably okay, but you probably won't get the marks they want. You'll just say it's below the cut of the significance level. And so you compare this to the significance level, and the significance level, if you're lower than that, then you reject the null hypothesis. Too low, reject the null. But the only reason we talk about all these null hypotheses is because we can't calculate that probability without picking a situation. So we pick one, and then we have to compare to it. It's a great big proof by contradiction, but using probabilities. And I have to say, honestly, it's very clever as a way of making decisions. They're really cool. And in fact, this year is the 100th anniversary of hypothesis testing. P-values were first published in 1925. Cool, huh? Yeah, so you'd think in all this time we'd have figured out how to teach it so that it wasn't so confusing. But, you know, honestly, some things are confusing because they're very clever. It's a very clever idea, and that's why it's so confusing. Yeah. But in my head, I hold on tight to this pick a null hypothesis, and then we're imagining all of the things that could have happened. And the only way to do that is to pick an answer. And so we've picked one. But this is how all hypothesis testing works. And the secret and most amazing bit of all of it is that it's possible, if you pick the right calculation for this thing, to know what this distribution is. So to be fair, anything that you could possibly write down about individuals or groups of individuals or calculate from groups of individuals, anything has a distribution. Like the big idea of the philosophy of statistics is that no matter what you calculate from your data, the universe has somewhere a big list of all the things that could be and how likely they all are. Like when you roll two ordinary six-sided dice, there is a list that says how likely all of the different options are, and rolling a 7 is the most likely one, right? And so that's there. But I could roll 7 dice, and I could do the calculation of the mean minus 2 of the minimum and times by the standard deviation. I could do whatever I want, and that would have a distribution. I just wouldn't know what it was. And what our friends in the past, Fisher and Gossett and Mann and Whitney, what they did is they figured out ways to do a calculation in such a way that we would know what this graph is. And that's so cool. Like, it's so cool. And that's why we keep mentioning these Z's and T's. If you do the calculation just the right way, then this is a Z distribution. If you do the calculation the right way, then this is a T distribution. Or if you do it the right way, then it's an F distribution or a chi-squared distribution. I think that's the coolest thing ever as a way of like answering this question. This question should be impossible because it wouldn't be possible to figure out what this graph is. But you can, and it's amazing. Anyway, that's something. Yeah. So the story goes that when you have a Z test or a T test, then you can calculate your test statistic, Z or T, and it will be equal to some estimate from the sample minus what the number is from the null hypothesis divided by a thing called the standard error. And they all look like that. And so if you know that that's the shape that it is, then you can set up a nice little table that will say in these situations, what's the sample estimate, what's the number from the null, and what's the standard error. And you can create this calculation. And this calculation will always be this shape. So for example, the z-test for one mean, we will have a z will be the sample mean minus the mean from the null hypothesis divided by the population standard deviation on root n, where x is the sample mean, mu naught is the number from null hypothesis, which was that mu is equal to mu naught. So in our question about the capacity of the bottles, that would have been 2 for 2 liters. And sigma is the population standard deviation, and n is the sample size. So the z-test for one mean is that. And when you imagine all of the things that could possibly be, if you live in null hypothesis land, you imagine all of the samples that you could have taken of size n, and you imagine all of the z statistics that could possibly happen, they come from a standard normal distribution with 0 in the middle. So z is distributed as a normal distribution with 0 and 1. Have you seen this symbol with a twiddle like that? Twiddle for distributed as? Okay, cool. And then your p-value will be like this area, like that. But in the z-test for a proportion, you know what? I'm not going to try and fit that on one page. That's a bad move. Look how much space this took. That's not going to work. And then the z-test for one proportion, it's still going to be this shape. And this is going to be the proportion from the sample. And this is going to be the proportion from the null hypothesis. And this is going to be a standard error. And a standard error almost always, nope, I won't say that. A standard error always has a square root in it. And what this is, oh, man, P naught 1 minus P naught on n, I believe. I think I'm right about that. And so this P hat is the sample proportion. This P naught is the proportion from H naught mu, not mu, P equals P naught. And n is the sample size. So the calculation is different because the situation is different, but the result is the same. It's still a normal distribution. And you'll still do the p-value the same way. And that's the cleverness of the people who have created these things, is they've figured out exactly what to put in these things so that even though you're in a different situation, it still comes out to be a Z after all. It's just super clever. But in the t-test for one mean, I reckon I can fit this in here. It's not a Z this time, it's a T, but it looks exactly the same except for one key difference. This one's got a sigma, this one's got an S. So in this one, S is the sample standard deviation. And it's a T, not a Z. And what T comes from is not a Z distribution, but a T distribution. That's why we've called it T. And it's the T distribution with n minus 1 degrees of freedom. Degrees of freedom is a silly word phrase, but we're stuck with it now. And it's still, do you know what? To the naked eye, it still looks exactly the same. But to the computer, the probabilities are different depending on what n is. But it's still the same thing. It's estimate minus thing from the normal distribution, from the null hypothesis divided by standard error. Once you get to the p-value, the result is the response is always the same. How are we feeling? Okay. I might as well write all the other ones down now that we're at it. So our t-test, the two-sample t-test. So you subtract the two sample means from the two different situations. And then you're interested in whether the means are the same. And then this is probably this. Yeah. Cool. Luckily, I did a seminar with this stuff in it like last week, so I can still remember. But I do know that it does have standard deviations in it. It's just like the normal single one. Because with the single one, if we square root that, you'll get S1, root S1 on n root N1, which is the same as the single t-test. So each part is separate there. Where x2, sorry. I like to do x2 minus x1 because it's normally after minus before. Because if you do anyway, that just makes more sense to me. So x2 is the mean in situation 1, and x1 is the mean in situation 2, and S1 is the sample standard deviation in situation 1, and S2 is the sample standard deviation in situation 2, and N1 is the sample size of the individual subjects in situation 1. In situation 1, and N2 is the sample size in situation 2. And I will say that the null hypothesis normally looks like this, where there's two different population means, or mu2 minus mu1 equals 0. That's why we put a 0 just here. Because if you look at this, this is x2 minus x1, that's mu2 minus mu1. And so the 0 is the number that goes in that spot. So it's important to pitch your null hypothesis in such a way that you can pick a number to go in this spot. And so we've picked 0 to go in that spot because the difference is 0. Yeah. Rightio. And the two-sample proportion test, here we go. Oh, sorry, that's not a Z, that's a T. What am I doing? That's a t, because it's a t-test. The z-test for two proportions is extremely similar. And in fact, I'll probably do exactly, oh no. Ah, it's not similar. Okay, that's okay. I thought what I would do, you know how this one I just copied what I had up here, but with S2 and S1? And I thought, oh, maybe what I'll do is I'll just copy this, but with a p hat 1 and a p hat 2. No, no. This has just got a, isn't it? Is this right? Oh, I know. Wait. I think it's this. Okay. Oh, right. You ready? This is so cool. Like, I know that that's the formula, and I will put that back, but in my head, it's this, where I've copied the thing that I would have done for the one proportion and done it with N1 and N2. But I've replaced the P naught with P hat in both of them. And so if you do some algebra, it'll come out to this. Right. Anyway, so this P2 hat is the proportion in situation 1, and the P1 hat is the proportion in situation 2, and N2 is the sample size in situation 2, and N1 is the sample size in situation 1. And P hat is a combined proportion if you combine the two situations into one big situation. And I can only do this with an example. It's too hard to do a formula for it. So e.g., situation 1 had like 20 out of 35, and situation 2 has like 10 out of 28, for example. And so this would mean that the P1 hat would be 20 out of 35, that fraction, and the P2 hat would be 10 out of 28, that fraction. But when you combine them into one big group, that's 30 out of 63. That's right, isn't it? So we add 30, take 2, yeah. And so the P hat is 30 out of 63. So that's how you do the P hat in this situation, because the story is that you're telling, like, the null hypothesis that we're imagining here, and I should say this here, H naught is that P1 hat is P2 hat, which is the same as P2 hat minus P1 hat is 0. The story is that if being in a different situation doesn't make a difference to the proportion you get, like doesn't make a difference to how likely that yes outcome is, because that's the question we're asking. Like we know that the research question is, does being in a different situation make a difference to how likely that outcome is? If it doesn't make a difference, then those two situations aren't really different from each other. They're really the same situation. So I can combine them into one giant group. That's why the P hat is the way it is. Because we are wondering about the null hypothesis land where the two groups aren't different to each other. Not really. And so we combine them into one giant group and it gives us the combined proportion. Yeah. I'm sure there's a word for it, but I call it the combined proportion because it makes sense to me that I combine the two groups. Now, I just want to check something. Are you allowed to take notes into your exam? How much do you get? One double-sided? Okay. So, right. Now, also, you used R Studio in this course, and you got R Studio to do things like the t-tests for two sample. R Studio did t-tests for you, right? But it didn't do proportion tests for you, no? It did chi-squared tests for you, but not z-tests for proportions. Okay, so in general, in this course, usually what that means is that anything that you did in R, then you need to know how to interpret what R tells you. And the exam will usually contain, there is the output from, here's the commands and here's the output from R. What does it mean? Like, have we rejected the null hypothesis or not? That sort of thing. If you didn't do it in R, you're going to have to know how to calculate it. And so since you didn't do the z-test for two proportions in R, you have to have this formula somewhere and know how to put the numbers in. That's how most people who run these stats courses think about it. So that's just some advice for the exam. It's much more important to have these formulas for the ones that you didn't do in R. But from a point of view of seeing this shape, it's useful to know. Because theoretically, in at least one past exam that I've seen in this course, so it was a long time ago now, they had done a t-test for two sample t-test and shown the output, but they've they've covered up the bit that told you what the t-statistic was and asked you to calculate it yourself from the data. They've told you what the means and standard deviations are and asked you to calculate this, just so that you can prove that you know how that formula works. But again, what? For those of you watching on the video, that wouldn't have meant anything to you, but the lecture theatre turned its screens off for reasons I don't understand. Yeah, so that's all I'm saying, is that you need to know that the formula's there, and I'd be sticking them on a cheat sheet or something if I were you. I mean, I've obviously taken pages and pages and pages to write this, but you don't have to. You might be able to remember what all of these symbols stand for and not put that bit in, right, and just put the formula in. So you need to put on the cheat sheet the things that are hard for you to remember, and some of the things will not be hard for you to remember. You don't have to put them on. And a lot of people put this in a table. And what they do is they just write a table that says sample estimate, and they put like X bar, P hat, X2 bar minus X1 bar, and whatever. And then they put another row with this one. They put another column with this one, so that you can make it from these details. I'm the sort of person who likes to put all the formulas in directly. So that's me. Have I got all the Z's and T's yet? The match pairs one, that's the last one. Now, your match pairs t-test is an extremely special case, because even though the original data, the original research question looks like this, everybody's in two different situations and you measure this outcome twice for every person. The actual data you use to do this t-test, the actual data the computer's using to do this t-test, is that you actually take this number for each person and you subtract them. So if you think about each individual person, there's a situation 1 number and there's a situation 2 number. Everybody's got both numbers, right? And then what you do is you do situation 2 minus situation 1, and everybody has a single number at the end. That's what you calculate. And in the data, you've got 3 columns. You've got your 2 original columns, and technically you're creating a 3rd column of data, which is the difference between them. And this, normally they call it D for difference. And so what it actually becomes is the D we're interested in if the best mean for the D is 0. Because if being in a different situation didn't really make a difference, then some people would be higher in situation 1 and lower in situation 2, whereas other people would be higher in situation 2 and lower in situation 1. And some people would give the exact same answer for both. But that's really rare to give the exact same answer to a numerical outcome. And so what we want is that the actual differences, the mean is 0. So this is the original question we asked, but because everyone's got both of these measurements, we can actually subtract them and produce this. And so that's why the t statistic in this situation is d bar minus 0 on the standard deviation of the d's on root n. This is the same as this. But what we've actually done when we do the match pairs t-test, what you've actually done is created an entirely new set of data by subtracting the two numbers that you have for each individual person. And so that's why it says when you look in the textbook or the notes, d bar instead of x bar, because this is x1 and this is x2, and we've made a whole new set of data. So if in essence, this is like x1, this is x2, and this is d, which is x2 minus x1. And so d bar is the mean of the differences. SD is the standard deviation of the differences. And N is the sample size. And you don't have to have a separate N for the two different situations because it's the same people twice. So they're just the same people again. Like you don't need a different N for that. Yeah, and the T comes from a T distribution with N minus 1 degrees of freedom. I missed something back there, just a second. The two sample t-test, I didn't say what the degrees of freedom of the t is. There is a degrees of freedom that goes here. You should just trust the computer to tell you what it is. Because there's a really wickedly horrible calculation that produces the correct number for DF. Though if you at a pinch, you can just pick the smaller of N1 minus 1 and N2 minus 1. Is that what they said in this course? So computer will tell you, or choose the smaller N minus 1 out of the N1 and the N2. So the computer will tell you, and it will actually have decimals in it. It'll be like 3.47 or something. Whereas it won't be that. It'll be more like it'll be it'll be similar to the average of these two things, but not quite exactly. Is that what it says? Is that what it says? You check it before? Yeah. Was that all right? Luckily, it hasn't changed too much since I did the course, but yeah. But if you are just getting your computer to do it, it will just tell you a number because it has its own calculation, which is kind of somewhere between the average of N1 minus 1 and N2 minus 1, but it won't be exactly. So if this group was size 30 and this group was size 28, no, it won't. Wow, no, it won't. It'll be just something ridiculous. Yeah, it's probably going to be closer to N1 plus N2 than anything else. But yeah, it'll just calculate something for you. Some weird ass average of the two of them. Okay. Yeah. So it is a classic exam question. It is a classic exam question for them to say, means and standard deviations of data as follows, and it'll say situation 1, situation 2, and the difference. And it'll calculate and it'll say the mean, 1.8, 2.7, and 0.9. And the standard deviation is, 1.1 and 0.9, 1.3 or something like that. And they'll give you this information. And technically with this information, and the sample sizes, well, they're all the same. Technically with this information, you could do a 2-sample t-test. But this information, you would do a matched pairs t-test. The most appropriate thing to do is the matched pairs t-test because you can. And so you go match pairs and use this and ignore this. Yeah. So that's the classic exam question where they give you the means and standard deviations of the 2 different columns separately, but you don't need that to do the matched pairs. Yeah. So cool. I will say that this will indeed work out to be that minus that, by the way. This will be that minus that. So that's just how means work. So they could theoretically not give you this number. You have to calculate it yourself. But the important thing is knowing the standard deviation of the difference, because that goes in this spot here, the SD. That's the important thing. So the most likely thing to do is actually they'll just give you the RStudio output for both options, and you'll have to pick the right one based on the story. How am I doing? 5 minutes. Okay, so let's see. What have we covered? We did all the Z's and T's, which means we're left with the chi-squareds. Oh no, there's one more T. I should really just bear with me. I'm going to number my pages. Plus, it's good for a lecturer to not talk the entire time. There is one more T. Did I just write 12? Yeah. There is a T in the regression. So when you do regression, if you're asking, is Y related to X, that's a good yes or no question. And when you do regression, you have something like this. Is that how they write it? Probably with a hat there. Anyway, it's approximately this. Maybe with an E at the end. All right, just this. With what? Is it an E? Is it an epsilon? Yep. Okay, cool. Right. So this is the original story. So this is a formula that allows you to calculate Y from X. That's what this does. So if Y was not related to X, then it would be impossible to calculate Y from X. And then there would be no X in this formula at all. And Y would just be some number plus some random stuff. And so if Y is not, so the null hypothesis is Y is not related to X, then X shouldn't be in that formula. Because it should be impossible to calculate Y from X if they're not related. And if x isn't in that formula, that means that this number must be 0. Because it would be 0 times x, and therefore there will not be an x there after all. So that means the null hypothesis is that beta 1 is 0. That's why the null hypothesis is what it is in regression. Because if they're not related, this formula shouldn't have an x, and making that 0 will remove the x. Yeah. And so the test statistic is the actual value of the sample value of beta 1 minus the hypothesis value of beta 1 over whatever the standard error of beta 1 hat is. And this thing, you look it up in the table in the regression output. So in the regression output, it will say something like intercept or constant. And it'll give you a table, right? Estimate, standard error, t-value, p-value, degrees of freedom probably. Something like that. That look about right? Oh, sadness. But there's a p though, right? They may call it significance. And this won't be called slope. It will be called whatever the x variable is called. So if this was like milligrams of chili powder and body temperature, this would say chili powder in this spot here. So this would be the x variable name. And so these will all have numbers in them. And this estimate here, that's what beta 1 hat is. And this is the standard error of beta 1 hat, just there. And this t-statistic will be that minus 0 divided by that. So in some exams, they have given you the table and they've blocked this out and you've had to calculate it yourself. Yeah. But it's the same shape, right? It's estimate minus number divided by a thing. And that's how they've calculated. And there is a formula for how to calculate this, but I don't think they give that to you, or they don't care. They might give it to you. But that's what computers are for calculating that sort of thing. Yeah. And it's the degrees of freedom is n minus 2. And the 2 is for these two rows. Yeah. So they are your T statistics and your Z statistics. There are only 3 others, which is the ANOVA and the there's probably an F statistic in multiple regression, but that's not examinable, so we won't worry about that. There is one more statistic, which is the F statistic in ANOVA and the chi-squared statistic in the chi-squared. And so I might as well just say them now. And I know I'm only supposed to finish at 11:30, but I'm just going to finish it before the next seminar starts at 2, because it's better than leaving it, not doing it. So I just want to check. Yep. Oh, cool. Thank you. If 2 events A and B are not independent, what's the smallest value of PA and B? Could you go through that one? I will not have time to go through that one, but please do visit the Maths Learning Centre, either online or face-to-face, and we can definitely talk about it there, because that's a straight-up probability question, and I have already gone over time and I haven't finished this one yet. Thank you for keeping an eye on that for me. Okay, so we did do all the T's and Z's. Yep. Man, Whitney, I don't even know how to calculate that test statistic. The computer does that for you. Yep. So that leaves chi-squareds and ANOVA. So ANOVA it'll produce a table, and you can read the ANOVA things from the table. So it will have probably groups, and probably error, and probably total. SS, DF, MS, and P. Pretty sure that's what the table will look like. Yeah. So just as an example, if I had this story and I had 3 groups like this, and let's say there's 30 people here and 10 people here and maybe 20 and 25 people here, for a total of 50, 75. What'll end up in this spot, this here will be 74. It will be the grand total n minus 1. And this here will be 2, which is the number of groups minus 1. There's 3 groups. And this here will be whatever's left between these. This will be 72. And then these 3 things have been calculated from the data. They are how far, there's just a calculation and involving how the squares of how far everything is from the group means. And this involves the squares of how everything is from the grand mean. And this is the squares of how every group mean is from the grand mean, and included at once for every participant. This is that divided by that. So if you do this divided by this, then you get this answer here. And this divided by this is this answer here. And then this divided by this is this answer here. So this one divided by this one produces this answer. And that's how the ANOVA is calculated. And it is like absolutely the cleverest thing you've ever seen. Like, and Fisher, who invented it, like, was very smug about ANOVA. Like, he was like, this is the best thing ever. I'm so clever. No, I'm not going to explain it. You're an idiot. Like, he was just so arrogant and smug about ANOVA. And to be fair, it's really clever. But to be fair to all of us, Fisher was not a nice person. But he was very clever, and ANOVA is just awesome. It's amazing. And then the p-value is the same, except I will say that the F distribution isn't like this. It's like this. It starts at 0, and there's nothing over this side. And when you do the p-value, it's not both sides, it's only on one side, because it's impossible for it to be negative. Yeah, so that's there. And the F statistic, F for Fisher, he named it after himself, is F, and it has 2 degrees of freedom. 2 and 72. So you take these 2 numbers and you put them here. Yeah. And, you know, with the T distribution, there's only one number to tell you which T distribution you have, but for the F distribution, there's 2. Yeah. And so that is what it is. That's ANOVA. And the null hypothesis is that the being in a different group doesn't make a difference to the outcome, which is saying that all the means are the same. So the null hypothesis is all means equal, and the alternative is that not all the means are equal. And it is 100% okay for you to write it in words. Totally okay for you not to actually say mu1, mu2, mu3, just write it in words. Yep. Officially, after you finish the ANOVA, you're supposed to do like these follow-up t-tests. these pairwise things. But I don't have time to deal with that. We'd have to have a look at what your course does, because every course does that differently. So, yeah. And then finally, the 2 chi-squared tests. I've said true independence in brackets, because if you say chi-squared test, you don't say independence, it's okay, because people just assume that it's this one. So the chi-squared test for goodness of fit, as I said, is for asking whether a particular set of proportions does a good job of predicting this categorical outcome. And what you do is you have a list of how many are in each category. And then you compare that to how many you would have expected in each category. So you say, so for example, like Coke, Fanta, Sprite, total, there's like 10 and 5 and 20. That's probably unrealistic, but it's what we've got now. So you have this table of data like this. And then you say, well, what if, can I make this a 3? Then you say, like, are all the proportions equal? And then what you would have expected would be 11, 11, and 11, because then they'd all be equal. And so what you do, damn it. So, yeah, that's right. And the total's still 33, right? So the way the goodness of fit test works is you go this minus this squared divided by this. So you do observe minus expected squared over expected. And you do that for everything. So this will be 10 minus 11 squared over 11. This will be 3 minus 11 squared over 11. This will be 20 minus 11 squared over 11. And then you add them all up, and that gives you a chi-squared stick, which is a number. But that's how you do the goodness of fit test. Again, very clever. Pearson, clever man. Much less arrogant than Fisher, but still very clever. And you have to look this up in a chi-square distribution, which looks quite like an F distribution. But the degrees of freedom this time is what you get when you remove one of these boxes, and it's how many boxes are left. So chi-squared with degrees of freedom, number of boxes minus 1. And when I say number of boxes, I'm not including the total. All right. And the p-value is the same, but the p-value is only this side. But the interesting thing about these last, the z's and t's, the p-values are on both sides. But for the chi-squareds and the f's, it's only on one side. Yeah. And then the very, very, very last one goes like this. And most people don't get you to do this one by hand. They get you to get the computer to do this for you. But in this one, it's more like this. You know, you've got some categories here and some categories here, and you're interested in whether being in a different category here is associated with this. And in that one, you have to make a two-way table. So this is like job 3. So I'm just making up a random I'm imagining that we've asked students and lecturers what their favorite drink is. And it's something like this, and you can set up a table and have how many, all the people are in here somewhere, and you can put the numbers in the spots. And there'll be totals. Let's keep the same numbers we had for this one. Something like that. So you can do totals this way, and you can do totals this way. So the big question is, how do you compare this to what would have happened if there was no relationship? But if there was no relationship, then whether you're a student or a lecturer is irrelevant, right? And so this is really just this. And we would have expected 30 out of 75. That fraction, we would have expected it in both positions. And so what you end up with, this is the observed one, this is the expected one, and the expected one would be student, lecturer, Coke, Sprite, Fanta. And the totals will be the same. And so what we're going to get in this spot is 32 out of 75. That fraction of 33 is what goes in this spot here. Because that's in this group, there's 32 out of 75, that fraction. We want that fraction of the 33 in this spot and that fraction of the 42 in this spot. And so this one will be 13 out of 75 times 33. And this one will be 13 out of 75 times 42. And this one will be 30 out of 75 times 33. And this one will be 30 out of 75 times 42. That's how you do the expected ones. And if you look very closely, it's the row total times the column total divided by the grand total. And then you still do the observed minus expected squared divided by expected, and then you add them all up. And that's still a chi-squared test. And the degrees of freedom is what you get when you remove one row and one column. And there's 2 boxes left. And so it's 2. So this degrees of freedom is boxes after remove a row and a column. So in this case, it's 2. But if this was a 3 by 3 box, you remove one row and one column, there's 4 left. And so the bigger the table is, the bigger that gets. There you go. That's the chi-squared test. So to be fair, the questions they often ask about these things are, here is what the computer gives you. It gave you a chi-squared distribution, it gave you a p-value, and you can interpret it from there. But sometimes they say, what is the expected contribution for the student Coke category? And you would go, aha, well, it's 32 out of 75 times 33, that number. So they'll often ask you what the expected number is just for one of them, so that you can prove that you know how that's done. Or they'll say, what's the degrees of freedom? And you'll go, 2. And they won't ask you to show working, you'll just write it down. Well, this one is working. So yeah, again, very clever. Pearson, very clever, did something very cool here. And these days, generally, we don't write all these things down. We just get R to do it for us. And it adds up all of these totals for us, and it calculates these for us. It's all great. Whereas even 20 years ago, you would have to calculate, you would have to do this calculation and then look it up in the probability table. And obviously 100 years ago, well, that would be even harder. Yeah, And in fact, in courses where they use Excel to do this instead of R, you have to do this calculation because Excel can't do it on its own. Excel can do a t-test, but it is not good at the chi-split test. But that's because Excel is designed for tracking profits and losses. So it's only designed for numerical outcomes. It's not really designed for categorical. Yeah. Well, there you go. That's the whirlwind tour of all of the hypothesis tests in this course. And so I will let you know before I turn off the video that at least in semester 1, 2025, I will be in the Maths Learning Centre most of the time when it's open. And if not, there will be someone there who knows about these things. And if they don't, they will find someone who does. So just be brave and go and talk to someone. Your exam's not for a little while yet. Just know that after the exams start, Maths Learning Centre changes to 1 p.m. to 4 p.m. Monday to Friday instead of 10 a.m. to 4 p.m. Monday to Friday. And I know that was in the email, but you've got to say it. Yeah. Well, thank you. That was a big question to be given, and I'm glad to have done it one more time. I hope that's useful to you. Thank you. I'll stop the recording now. No, wrong button.